Lean Six Sigma Black Belt. Video Module FMEA, Failure Modes and Effects Analysis. Welcome to this deep dive into Failure Modes and Effects Analysis, or FMEA, a critical tool for black belt practitioners. This slide sets the tone for our session. As you can see from the title, we are going beyond the basics to understand FMEA in its full depth. Whether you're from manufacturing, services, IT, or healthcare, FMEA helps you anticipate what could go wrong, assess the impact, and prioritize action. The visual elements here, pie charts, line graphs, dashboards, and database stacks, signify that FMEA is a data-driven, analytical, and highly structured method. It's about identifying potential failure modes, quantifying their effects, and reducing the risk before issues reach the customer. Throughout this session, we'll look at how to fill out FMEA templates, calculate risk priority numbers, and most importantly, how to translate this analysis into preventive action. So buckle up for a session designed to empower you to drive quality, safety, and performance improvements using FMEA. Let's start by understanding what is FMEA. FMEA stands for Failure Modes and Effects Analysis. It is a structured, team-based approach used to proactively identify and address potential failures in a process, product, or system before they happen. You can see from the colorful steps on this slide that FMEA follows a logical flow. 1. Identify ways a process, product, or system might fail. This is where the team brainstorms all possible failure modes. Whether it's a component breaking, a process step being skipped, or a software crashing, we want to capture everything that could go wrong. 2. Evaluate the impact of each failure. Next, we assess how bad each failure could be. Will it affect customer satisfaction? Will it create rework, delays, or even safety issues? 3. Prioritize the risks based on severity, frequency, and detectability. This is where we calculate the risk priority number, RPN. We give scores to each failure mode based on how serious it is, how often it happens, and how easily it can be detected before reaching the customer. 4. Define and implement corrective actions to reduce or eliminate risk. Finally, based on the priority, we take actions to reduce the risks. This could be process redesign, extra checks, or automation. The character on the right side represents that common confusion or curiosity many people have about what exactly FMEA is. But with this structured approach, we'll clear that up. So essentially, FMEA helps us move from uncertainty and guesswork to informed, risk-based decision-making. Now that we understand what FMEA is, let's look at the different types of FMEA and where they are applied. As you can see in this table, FMEA is not a one-size-fits-all approach. It is tailored depending on the phase or function within the system or process you're analyzing. Let's walk through each type. 1. Design FMEA, DFMEA. This is used during the design phase of a product or system. Its purpose is to identify potential failures in product design before the product is built. For example, if you're designing a car's braking system, DFMEA will help assess what could go wrong in that design, like material strength, component tolerances, or operating conditions. 2. Process FMEA, PFMEA. This type is applied to manufacturing or business processes. PFMEA helps identify where the process could fail, such as incorrect machine setup, operator errors, or poor raw material quality. It's widely used in production lines, service workflows, and quality control procedures. 3. System FMEA. This form looks at the system as a whole, particularly at system-level functions and potential failures, that occur due to interactions between subsystems. For example, in an aircraft, System FMEA might assess what happens if communication between the flight control and navigation system fails. Fourth service FMEA. This is designed specifically for service delivery environments such as call centers, hospitals, or logistics operations. It evaluates risks like delayed service, miscommunication, or incorrect order processing, all of which impact customer satisfaction. Each type of FMEA has a similar structure, but is adapted to the unique risks of that environment. Choosing the right type ensures you're targeting the most relevant failure modes for that situation. Before we get hands-on with an FMEA worksheet, it's important to first understand the key terminology used throughout the FMEA process. Let's walk through each of these terms briefly. 1. Failure mode. This refers to the way something could go wrong. It's the specific manner in which a process, product, or component could fail. For example, a valve might stick, a form might be submitted incorrectly, or a step could be skipped. Second effect. This is the consequence of the failure. What happens when the failure mode occurs? It could be a delay in delivery, a defective product reaching the customer, or a safety hazard. 3. Cause, the root cause of the failure mode. Why did the failure happen? This could be due to improper training, worn-out parts, missing documentation, or poor design. 4. Severity, S. This tells us how serious the effect of the failure is. It's scored typically on a scale from 1, least severe, to 10, most severe. 5. Occurrence, O. This measures how likely the failure is to happen. Again, it's rated on a scale, where higher numbers indicate more frequent failures. 6. Detection, D. This measures how likely we are to catch the failure before it impacts the customer. A low score means high detectability. We can easily catch it, and a high score means it's hard to detect. 7. RPN, Risk Priority Number. This is a numeric score calculated by multiplying severity times occurrence times detection. The higher the RPN, the higher the risk, and the more urgently it needs to be addressed. 8. Action Priority, AIAG-VDA. This is a more recent approach introduced by automotive industry standards. Instead of relying only on the RPN number, this method uses a structured table to prioritize actions based on severity, occurrence, and detection in a more meaningful way. Understanding these terms is critical. They form the backbone of how we evaluate and respond to risks in any FMEA. This slide connects the use of FMEA with the DMAIC phases of a Six Sigma project, helping us understand where and how FMEA fits into the problem-solving lifecycle. Let's look at each phase where FMEA is typically applied. 1. Analyze phase. In this phase, we use FMEA to identify potential failure modes related to the root causes we've uncovered. After performing root cause analysis using tools like Fishbone or 5 Whys, we apply FMEA to document all possible ways those root causes might manifest as failures in the process, product, or service. 2. Improve phase. Once potential solutions are identified, FMEA is again used, this time to assess the risks associated with each proposed solution. For example, if we decide to automate a process step, FMEA helps us foresee what could go wrong with that automation, such as integration errors or training gaps, so that we can proactively mitigate those risks. 3rd control phase. After improvements are implemented, we update the FMEA to reflect the new process conditions. This ensures that O. We capture any new risks, O. Verify that past risks have been addressed, O. And use it as a living document to monitor stability over time. FMEA is not a one-time tool. It's a continuous risk management approach that should evolve along with your process. The red stamp graphic emphasizes that FMEA is an authoritative, structured tool, not optional, but essential for robust process management and long-term success. This slide gives us a clear step-by-step process for conducting an effective FMEA. Think of this like climbing a staircase. Each step builds upon the previous one and takes you closer to risk reduction and process reliability. Let's go through each step. Step 1. Define scope and assemble a cross-functional team. FMEA is a team-based activity. We begin by clearly defining the boundaries, what process, product, or system we are analyzing. We also assemble a team with diverse knowledge, engineering, quality, operations, and even customer-facing roles. Step 2. Map process steps. Use SIPOC or process flow. We visualize the process using tools like SIPOC or detailed flowcharts. This helps break the process into manageable steps for failure analysis. Step 3. For each step, list potential failure modes. Now, for every step in the process, we brainstorm what could possibly go wrong. These are your potential failure modes. Step 4. Identify effects and causes. Once failure modes are identified, we determine what the effect of that failure is and what the root causes might be. This is the foundation for understanding risk. Step 5. Rate severity S, occurrence O, detection D, from 1 to 10. Each failure mode is rated on 3 scales. Severity, how bad is the effect? Occurrence, how likely it is to happen? Detection, how easily we can detect it before it reaches the customer. Step 6. Calculate RPNS times O times D. Multiply the 3 values to get the risk priority number. Higher RPN means higher risk and therefore higher priority for corrective action. Step 7. Use action priority if applicable. AIAG VDA approach. For advanced users or regulated industries, like automotive, we use action priority tables, which provide a more structured way of prioritizing actions compared to RPN alone. Step 8. Recommend and assign actions. For high-risk failure modes, we identify improvement actions, like adding error proofing, updating SOPs, or retraining staff. Owners are assigned to ensure accountability. Step 9. Re-rate after actions taken. Once actions are completed, we come back to the FMEA and rescore the severity, occurrence, and detection. This tells us whether risk has been effectively reduced. This process is not just a document. It's a living risk management tool that should be updated regularly as processes evolve. This slide shows a real-world example of how process FMEA, PFMEA, can be applied in a service industry context, specifically the loan approval process. Let's walk through each row of this table to understand how FMEA is used here. Step 1. Credit check. Failure mode. Credit check is missed due to system lag. Effect. The loan gets approved for an ineligible customer, which is a critical risk for any financial institution. Cause. The root cause is a system timeout. Ratings. O severity, 9. High impact. Ineligible loan approval can lead to major financial losses. O occurrence, 6. System timeouts are not uncommon. O detection, 4. Failure might not be caught early. RPN, 9 times 6 times 4 equals 216. This is a high-risk item and needs immediate corrective action, possibly upgrading the system or adding validation checks. Step 2. Document review. Failure mode. Wrong document is verified. Effect. This leads to rework and delay, which affects customer satisfaction and process efficiency. Cause. Manual error may be due to lack of training or unclear instructions. Ratings. O severity equals 7. O occurrence equals 5. O detection equals 5. RPN equals 7 times. 5 times 5 equals 175. This is still a moderately high-risk area that warrants improvement, perhaps through automation or a second-level review. This example clearly shows how FMEA is not limited to manufacturing. It is equally powerful in service processes. Whether it's finance, healthcare, or customer service, FMEA helps us prevent failures before they cause harm. This slide highlights some of the most common mistakes or pitfalls that teams fall into when conducting FMEA. These pitfalls can undermine the effectiveness of the entire exercise. Let's walk through each one. Vague failure descriptions. System error. One of the biggest issues is using generic or unclear language. For example, writing system error doesn't tell the team what exactly went wrong. Was it a timeout? A software bug? A login failure? Be specific. A good FMEA clearly defines the failure so that root causes can be addressed. Copy-pasting ratings without team discussion. Sometimes teams reuse old severity, occurrence, or detection ratings without re-evaluating them for the current context. This defeats the purpose of FMEA being a team-based analytical activity. Make sure you involve all key stakeholders when assigning ratings and justify them based on current data. Not revisiting FMEA post-improvement. Once improvements are implemented, many teams forget to update their FMEA, but this is essential. You need to recalculate RPN or reassess action priority based on the new process conditions to verify whether the risk has actually reduced. Assuming perfect detection systems. This is a common overconfidence trap. Assuming that the detection systems in place, like alarms, checks, validations, will always work. In reality, no detection method is foolproof. Always assign a realistic detection score based on data, audits, and past failures. In summary, FMEA is only as good as the effort and honesty the team puts into it. Avoiding these pitfalls ensures that your FMEA is reliable, actionable, and effective in risk reduction. This slide lists some of the most common pitfalls teams encounter when doing FMEA. These issues often lead to poor quality analysis and ineffective risk mitigation. Let's walk through each one. Vague failure descriptions. System error. This is one of the most frequent issues. Using unclear terms like system error or process breakdown without specifying what exactly failed. We need precise and actionable failure modes. For example, login timeout due to session expiry is much clearer than just system error. Copy-pasting ratings without team discussion. Sometimes, teams reuse past severity, occurrence, or detection ratings or assign scores without actually discussing the rationale. FMEA is supposed to be a collaborative tool. Team consensus and discussion are critical to make sure the ratings reflect the current context. Not revisiting FMEA post-improvement. After actions are implemented, FMEA should be updated, but often it's forgotten. If you don't re-rate severity, occurrence, or detection, you won't know whether your actions truly reduce the risk. This makes your improvement efforts incomplete. Assuming perfect detection systems. No detection method is perfect, not even automation. Many teams assign detection scores as if the control will catch everything. We must be realistic about what our detection controls can actually do, based on audit data, past misses, or simulation results. By avoiding these pitfalls, you ensure your FMEA is not just a formality, but a powerful tool for proactive risk prevention. This slide presents advanced practices that take your FMEA from a basic checklist to a powerful integrated risk management tool. Let's explore each of these advanced practices. Link FMEA to the control plan. One of the best practices is to ensure that the metrics and response actions identified in the FMEA are directly reflected in the control plan. For example, if your FMEA identifies a failure mode with a high severity score, the control plan should include monitoring of that step, control limits, and predefined responses if those limits are breached. This alignment creates continuity between risk identification and process control. Use software tools, e.g., APIS, XFMEA, Excel-based tools. While Excel is still commonly used, dedicated FMEA tools like API's IQRM or XFMEA can streamline the process. These tools help automate scoring and prioritization, maintain traceability, enable version control and change tracking. They're especially useful in regulated industries or complex projects where risk needs to be documented and maintained in real time. Update FMEA after process change, audit, or customer complaint. FMEA is not a one-time document. It must be updated whenever there's a process change, non-conformance, audit finding, or even a customer complaint. This ensures the risk assessment reflects real-world conditions and helps maintain the relevance of your mitigation plans. Integrate with QMS and risk registers. The final best practice is to connect your FMEA with the organization's quality management system, QMS, and formal risk registers. This integration ensures visibility to leadership, alignment with compliance and governance, and the ability to track, audit, and report risks across the organization. Implementing these advanced practices transforms FMEA from just a reactive tool into a proactive, system-wide safety net. As we wrap up our session on FMEA, here are some final takeaways to remember. These points capture the essence of why and how FMEA adds value to your quality and process improvement efforts. Point 1. FMEA helps prevent failures before they happen. This is the core strength of FMEA. It's a proactive tool, not reactive. It helps us identify what could go wrong and take action before customers or operations are impacted. In a world where customers expect zero defects, this foresight is essential. Point 2. It's both a thinking tool and an action guide. FMEA helps teams think critically and collaboratively. It goes beyond just documentation. It drives discussion, decision-making, and action based on structured risk analysis. Point 3. Use it iteratively. Update it as your process evolves. FMEA is not fill and forget. Every time there is a process change, audit finding, new product version, or customer feedback, go back to the FMEA. It should evolve along with your process so it remains accurate and useful. Point 4. A good FMEA equals less firefighting and more proactive improvement. When you apply FMEA effectively, you'll find your team spends less time fixing problems and more time preventing them. This leads to better quality, fewer complaints, and smoother operations. So in short, a well-executed FMEA is not just a formality, it's a strategic tool for sustainable improvement.